CS stage with source degradation. In some applications, the square law dependence of the drain current upon the overdrive voltage introduces a non-linearity, making it desirable to soften the device characteristic. In session, we noted the linear behavior of a CS stage using a diode connected load. Alternatively, as depicted in figure, this can be accomplished by placing a degeneration resistor in series with the source terminal. Here, as Vn increases, so do ID, and the voltage drop across RS. Here you can see the figure CS stage with source degeneration, that is, a fraction of Vn appears across the resistor rather than as the gate source overdrive, thus leading to a smoother variation of ID. From another perspective, we intend to make the gain equation function of GM gain equation a weaker function of GM. Since V out is equals to minus IDRD, the non-linearity of the circuit arises from the non-linear dependence of ID upon Vn. We note that dou V out by dou Vn equal to minus dou ID by dou Vn RD, and define the equivalent transconductance of the circuit as Gm equal to dou ID by dou Vn. Now assuming ID is equals to f of V of G of S, f of VGS, we write Gm equal to dou ID by dou Vn equal to dou F by dou VGS into dou VGS by dou Vn. Since VGS is equals to minus Vn, since VGS is equals equal to Vn minus IDRS, we have dou VGS by dou Vn is equals to 1 minus RS dou ID by dou Vn, obtaining Gm equal to 1 minus RS dou ID by dou Vn into dou F by dou VGS. But dou F by dou VGS is the transconductance of M1, and Gm equal to Gm by 1 plus Gm RS. The small signal voltage gain is thus equal to AV equal to minus GMRD is equals to minus GMRD by 1 plus GMRS. The same result can be derived using the small signal model of figure B. Equation implies that as RS increases, GM becomes a weaker function of GM and hence the drain current. In fact, for RS very much greater than 1 by GM, we have GM similar to 1 by RS, that is the delta ID similar to delta Vn by RS, indicating that most of the change in Vn appears across RS. We say the drain current is a linearized function of the input voltage. The linearization is obtained at the cost of lower gain and higher noise. Here you can see the figure small signal equivalent circuit of a degenerated CS stage. For our subsequent calculation, it is useful to determine Gm in the presence of body effect and channel length modulation. with the aid of the equivalent circuit shown in figure. We recognize that the current through Rs equals R out, and therefore V in equal to Vi plus I out Rs. Summing the currents at node X, we have I out is equal to GMV1 minus GMB Vx minus I out Rs by R naught is equals to GMV in minus I out Rs plus GMB minus I out Rs minus I out Rs by R naught. It follows that GM is equals to I out by V in is equals to GM R naught by Rs plus 1 plus GM plus GMB Rs R naught. Let us now examine the last signal behavior of CS stage with Rs equal to 0 and Rs not equal to 0. For Rs equal to 0, our derivations in chapter indicate that ID and GM vary as shown in figure A. For Rs not equal to 0, the turnout behavior is similar to that in figure A, because here you can see the figure. Drain current and transconductance of a GS device A without and B with source degeneration at low current levels 1 by GM very much greater than Rs, and hence GM is similar to GM figure B as the overdrive, and therefore GM increase the effect of degeneration. 1 plus GM Rs in equation becomes more significant for large values of Vn if M1 is still saturated. ID is approximately linear and GM approaches 1 by Rs. Equation can be rewritten as AV equals to minus RD by 1 by GM plus Rs. This result allows for formulating the gain by inspection. First, let us examine the denominator of equation. The expression is equal to the series combination of the inverse transconductance of the device and explicit resistance seen from the source to ground. We call the denominator the resistance as seen in the source path, because if, as shown in figure, we disconnect the bottom terminal of Rs from ground and calculate the resistance seen looking up while setting the input to 0, we obtain Rs plus 1 by GM. Figure resistance seen in the source path, nothing that the numerator of equation is the resistance seen at the drain. We view the magnitude of the gain as the resistance seen at the drain node divided by the total resistance in the source path. This method greatly simplifies the analysis of more complex circuits. Another important consequence of source degeneration is the increase in the output resistance of the stage. We calculate the output resistance first with the aid of the equivalent circuit shown in figure. Note that body effect is also included to arrive at a general result. Here you can see the figure equivalent circuit for calculating the output resistance of a degenerated CS stage. Since the current through Rs is equals to Ix, V1 is equal to minus Ix Rs, and the current flowing through R0 is given by Ix minus Gm plus Gmb. V1 is equals to Ix plus Gm plus Gmb Rs Ix Adding the voltage drop across R0 and RS, we obtain R0 into Ix plus GM plus GMB into RS Ix plus Is RS is equal to Vs. It follows that Rout equal to 1 plus GM plus GMB RS R0 plus RS is equals to 1 plus GM plus GMB R0 RS plus R0. Since typically GM plus GMB are not very much greater than 1, we have R0 similar to GM plus GMB R0 RS plus R0 is equals to 1 plus GM plus GMB RS R0 RS into R0, indicating that the output resistance has increased by a factor of 1 plus GM plus GMB RS. This is an important and useful result. To gain more insight, let us consider the circuit of figure with RS equals 0 and RS greater than 0. If RS equals 0 and GM V1 is equals to GMB, VBS is equal to 0 and Ix equal to Vx by R0. On the other hand, if RS greater than 0, we have Ix RS greater than 0 and V1 less than 0, obtaining negative GM V1 and GMB VBS. Thus the current supplied by Vx is less than Vx by R0. The relationship in equation can be derived by inspection as shown in figure A. We apply a voltage to the output node, change its value by delta V and measure the resulting change delta I in the output current. Since the current through RS must change by delta I, we must compute the voltage across RS to this, and we draw the circuit as shown in figure B, and note that the resistance in looking into the source of M1 is equal to 1 by GM plus GMB, thus arriving at the equivalent circuit in figure C. Here you can see the figure. A, change in drain current in response to change in applied voltage to drain. B, equivalent of A. C, small signal model. The voltage change across RS is therefore equal to delta V RS equal to delta V into 1 by GM plus GMB parallel to RS by 1 plus 1 by GM plus GMB parallel to RS plus R0. The change in the current is delta I equal to delta V RS by RS equal to delta V into 1 by 1 plus GM plus GMB RS into R0 plus RS, that is delta V by delta I is equal to 1 plus GM plus GMB RS R0 plus RS into R0 plus RS. With the foregoing developments, we can now compute the gain of a degenerated CS stage in the general case, taking into account both body effect and channel length modulation in the equivalent circuit depicted in figure. The current through RS must equal that through RD, that is minus V out by RD. Thus the source voltage with respect to ground and the bulk is equal to minus V out RS by RD, and hence V1 equal to V in plus V out into RS by plus V out RS by RD. The current through R0 can therefore be written as I R0 equal to minus V out by RD minus GM V1 plus GMB VBS is equal to minus V out by RD minus GM V in plus V out RD by RS by RD plus GMB V out into RS by RD. Here you can see the figure. Small signal model of degenerated CS stage with finite output resistance. Since the voltage drop across R0 and RS must add up to V out, we have V out equal to I R0 minus V out by RD into RS equal to minus V out by RD into R naught minus GM plus V in plus V out into RS by RD plus GMB V out into RS by RD R naught minus V out into RS by RD. It follows that V out by V in equal to minus GM R naught RD by RD plus RS plus R naught plus GM plus GMB RS R naught to gain more insight into the result. To gain more insight into the result, we recognize that the three terms in the denominator, namely RS R naught GM plus GMB RS R naught, represent the output resistance of a MOS device degenerated by a resistor RS originally derived in equation. Let us now rewrite equation as AV is equals to minus GM R naught RD into RS plus R naught plus GM plus GMB RS R naught by RD plus RS plus R naught plus GM plus GMB RS R naught into 1 plus into 1 by RS plus R naught plus GM plus GMB RS R naught is equals to minus GM R naught by RS plus R naught plus GM plus GMB RS R naught into RD RS plus R naught plus GM plus GMB RS R naught by RD plus RS plus R naught plus GM plus GMB RS R naught. The two fractions in equation represent two important parameters of the circuit. The first is identical to that in equation, that is the equivalent transconductance of a degenerated MOSFET, and the second denotes the parallel combination of RD and RS plus R naught plus GM plus GMB RS R naught, that is the overall output resistance of the circuit. The above discussion suggests that in some circuits it may be easier to calculate the voltage gain by exploiting the following lemma. A linear circuit, the voltage gain is equal to minus GM R out, where GM denotes the transconductance of the circuit when the output is shortened to ground, and R naught and R out represents the output resistance of the circuit when the input voltage is set to 0. Figure A. The lemma can be proved with the aid of figure by noting that the output port of a linear output of a linear circuit can be modeled by a Norton equivalent, that is the output voltage is equal to minus V out minus I out R out, and I out can be obtained by measuring the short circuit current at the output. Here you can see the figure modeling output port of an amplifier by a Norton equivalent, defining GM equal to I out by V in. We have V out equal to minus GM V in R out. This lemma proves useful if GM and R out can be determined by inspection. Thank you.